This is my third lecture on multicollinearity. The problem of multicollinearity exists when two or more regressor variables are dependent, or you can say that when two or more random regressor variables are linearly dependent. Okay. So, in the last class we talked about the different techniques to detect multicollinearity. We learned about examination of correlation matrix, and also we learned about the eigensystem analysis of X prime X matrix or the correlation matrix. Okay, so first I will recall the eigensystem analysis we learned in the previous class. Well, what we do here is that we first compute the k minus 1 eigenvalues of the X prime X matrix, and then we compute the condition number, which is k, denoted by k, equal to lambda max by lambda minimum, and the larger value of k indicates the severe problem with multicollinearity. As a general rule, this is what we talked in the last class. If k is less than 100, then that indicates no serious problem with multicollinearity. If k is between 100 and 1000, then that indicates moderate to strong multicollinearity. But if k is greater than 1000, then that indicates a severe problem with multicollinearity. Okay. So, this is how we condition number is used to detect the multicollinearity. The advantage of this eigensystem analysis is that it not only detect a multicollinearity, it can measure the number of linear dependencies in the correlation matrix. Okay. And also it can determine, or it can identify the nature of linear dependencies between the regressors. So, for that what we do is that we compute the condition indices. Here is the condition indices kj. Kj is associated with the jth regressor. So, kj is lambda maximum by lambda j, right, and the number of kj greater than 1000 is a useful measure of the number of linear dependencies in X prime X. Okay. And then I illustrated this result using the Webster data. This is the Webster data I talked about in the previous class. We have 6 regressors, the response variable, right, and I refer this data as Webster data. Now, the eigenvalues for the eigenvalues of X prime X matrix or the correlation matrix for the Webster data is here, lambda 1, lambda 2, lambda 3, lambda 4, lambda 5, lambda 6, and the smallest eigenvalue is this is this one, which is close to 0. Now, we compute the condition number. See, the condition number is 2188, which is greater than 1000. So, this condition number indicates the presence of severe multicollinearity in the Webster data. So, next what we will do is that we will compute the condition indices also. Since we know the eigen values, we can compute the condition indices, right. So, the condition indices are, what is condition indices? Kj, Kj is equal to lambda max by lambda j. Okay. So, K1 is lambda max is 2.4288 by lambda 1 is basically maximum. So, lambda 1 is 2.4288, which is equal to 1. So, K2 is lambda max, which is equal to 2.4288 by lambda 2, which is equal to 1.5462 equal to 1.57. Similarly, you compute K3 which is equal to lambda max by lambda 3 is equal to 7.88. K4 is lambda max by lambda 4, that is 2.4288 by lambda 4 is 0.9221, which is equal to 2.633. Okay, so I did some mistake here. This is K3, this is K3, this is K5. Okay, anyway, you can compute what is K3, and then K4 is equal to 3.05, K5 is equal to this quantity, and K6 is equal to 2188.11. Okay. Now, we know that here only one condition index exceed 1000, right, that is K6. So, we conclude that there is only one near linear dependence in the data. Because we I mentioned before that the number of Kj greater than 1000, that measures the number of linear dependencies in the data, and since here only one Kj, that is K6 is greater than 1000, that is why the number of linear dependence or dependencies is equal to 1 only. Well, now what will, I mean, this technique has lot of advantages, like it not only detect the presence of multicollinearity, it can measure the number of linear dependencies in the data, and also it can identify the nature of the linear dependencies. Okay. So, now we will explain that portion. Here eigensystem analysis can also be used to identify the nature of linear dependencies in data. Okay. So, let me explain this portion first. The correlation matrix x prime x may be decomposed as, x prime x you can write or decompose as x prime x is equal to t d t, okay, where D is a diagonal matrix whose main diagonal elements are the eigenvalues. Okay. So, D equal to diagonal lambda 1, lambda 2, lambda k minus 1. Okay. And T is equal to T is a k minus 1 cross k minus 1 matrix, and whose the columns of this T matrix they are T 1, T 2, T k minus 1. So, here this T I is the eigenvector associated with lambda I, okay, where T I is equal to A 1, A 2, A k minus 1 is the eigenvector associated with eigenvalue lambda I. Right. Okay. So, this is the decomposition of the correlation matrix. Now, if lambda j, if the eigenvalue lambda I is close to 0, the elements of the associated eigenvector, that is T I, describe the nature of linear dependence. Okay, so the nature of this linear dependence is like A1 x1 A2 x2 plus A k minus 1 x k minus 1 is equal to 0. So, this coefficient of the regressors regressor variables A1, A2, A k minus 1, they are basically the elements of T I. So, T I, this is the eigenvector associated with lambda I, and lambda is very close to 0. So, T I is the eigenvector associated with lambda I, and T I is equal to A 1, A 2, A k minus 1. Right. So, okay, so maybe just I will just give the little bit motivation behind this. You know, if lambda I is close to 0, then the condition index associated with lambda I is large. I mean, that would be greater than 1000, and and then you will get a linear. Okay, you will get one linear dependence between the regressor variables associated with lambda I. So, that is why, you know, as I mentioned before also, you know, that the number of condition indices greater than 1000, that measures the number of linear dependencies in the data, and corresponding to each lambda I for which the condition index is greater than 1000, you will get a linear dependence, or you can identify a linear dependence between the regressor coefficient between the regressors. Okay. Let me explain, I mean illustrate this thing using the Webster data. Okay. Here the smallest eigenvalue is lambda 6, which is equal to 0.0011, and the associated eigenvector, that is say T 6 is equal to minus 0.447 minus 0.421 minus 0.541 minus 0.573 minus 0.006 minus 0.002. So, this is the associated eigenvector corresponds to lambda 6, and then the nature of linear dependence is minus 0.447 x 1 minus 0.421 x 2 minus 0.541 x 3 minus 0.573 x4 minus 0.006 x5 minus 0.002 x6 equal to 0. And from here, since these two are very small, we can ignore x5 and x6 from this equation, and this implies that x1 is equal to minus 0.941 x2 minus 1.21 x3 minus 1.28 x4. Okay, so this is the linear dependence between the regressor x1, x2 and x3 and x4, and this linear dependence is associated with lambda 6, right. And if you have more eigen value which are close to 0, corresponds to each lambda I mean which are very small or which are close to 0, you will get a linear dependence like this. Okay. So, what we learned from this eigen system analysis is that it can detect the presence of multicollinearity, it can measure the number of linear dependencies in the data, and also it can identify the nature of linear dependencies in the data. Okay. So, next we move to the variance inflation factor. This is another way to to detect the presence of multicollinearity. Okay. This is called variance inflation factors. Okay. So, first we will recall the variance of ith regressors. Variance of the ith regressor coefficient variance of ith regressor coefficients mean variance of the least square estimate of ith regressor coefficient beta I hat. We know that this one is equal to sigma square x prime x inverse the ith element of x prime x inverse, right. Now, this can be it can be proved that this the ith element is equal to 1 by 1 minus Ri square sigma square here, right. Now, what is this Ri square? Ri square is the coefficient of multiple determination when xi is regressed on the remaining regressors, right. Now, see if the ith regressor xi is nearly orthogonal to the remaining regressor. Here this nearly orthogonal, I mean that if the ith regressor is independent of the remaining regressors, then Ri square is small and 1 by 1 minus Ri square is close to unity. Well, so the meaning of this one is that xi is nearly orthogonal to the remaining regressors. That means xi is independent of the remaining regressors. That means there is no linear dependence associated with xi. Okay, I mean xi can't be represented in terms of the linear combination of the other regressors. Then the coefficient of multiple determination when you are regressing xi on the remaining regressors, the coefficient of multiple determination will be small, and the value of 1 by 1 minus r square is close to unity, and the variance of beta I hat is going to be sigma square, close to sigma square. Now, if xi is nearly linearly dependent on some subset of the remaining regressor, Ri square value will be near to close to 1. Okay. Ri square is near unity, and 1 by 1 minus Ri square is large. So, the meaning of this xi is linearly dependent on some subset of the remaining regressors. That means there is a linear dependence between xi and some subset of the remaining regressors. If some linear dependence is there between xi and some subset of the remaining regressors, that means xi can be represented in terms of as a linear combination of some subset of the remaining regressors. Well, so which implies that Ri square, which is the coefficient of multiple determination when xi is regressed on the remaining regressors, is will be large, and that will be close to unity, and that implies that the value of 1 by 1 minus Ri square is large. That ultimately if there is a linear dependence in the data between the regressors, then the variance of beta I hat is going to be large, because this factor is going to be large. Well, so this factor this 1 by 1 minus Ri square, well, let me write here. So, variance of beta I hat is equal to sigma square into 1 by 1 minus r I square, right, and this quantity, this factor, this can be viewed as the factor by which the variance of beta I hat is increased due to linear dependence among the regressors. Right. Well, so if there is a linear dependence between xi and a subset of the remaining regressors, then the value of this is large. Okay, then the variance of beta I hat is also large. Now, if xi is independent of the remaining regressors, or I said that it is, if it is nearly orthogonal to the remaining regressors, then this value, this factor is close to 1, and the variance of beta I hat is almost equal to sigma square, right. So, the variance inflation factor VIF associated with regressor xi is defined by VIF I, which is equal to 1 by 1 minus r I square. And obviously, large value of VIF I indicates possible multicollinearity associated with xi. The meaning of this one is that, if multicollinearity associated with xi, that means this will, if this is large, that means there is a linear dependence between xi and a subset of the remaining regressors, then only the value of this one is going to be large. So, the large value of VIF I indicates possible multicollinearity associated with the regressor xi. Okay. Now, in general, VIF I greater than equal to 5 indicates possible multicollinearity problem, and VIF I greater than or equal to 10 indicates that multicollinearity is almost certainly a problem. Okay, so this is how the variance inflation factor associated with the ith regressor can be used to detect the multicollinearity. Okay. So, this technique, variance inflation factor can determine can detect the problem of multicollinearity, but of course, it can't identify the nature of multicollinearity. So, uh, eigensystem analysis is a better technique because it can detect the multicollinearity, it can measure the number of linear dependencies in the data, and also it can identify the nature of linear dependencies in the data. Okay. So, next we will be talking about uh, you know if you detect that there is multicollinearity in the data, then how to deal with multicollinearity. Okay. So, we will be talking about several techniques to deal with multicollinearity, right. So, dealing with the first technique is collect additional data. Well, collecting additional data has been suggested as the best method of dealing with multicollinearity. Okay, so this is perhaps the best way to deal with multicollinearity. What it says is that, let me illustrate this one little bit. Suppose you have you are in the multiple linear regression model, and suppose you have only two regressors, x1 and x2, and the response variable y, and you have n data points. Okay. So, you have some data, you have n data. Now, you have detected that the multicollinearity exists in this data. That means, here we have only two regressors, that means x1 and x2, they are linearly dependent. So, what we do is that we collect some more data, say another m data, to break the existing multicollinearity in the present data. Okay. So, what we do is that so these two are regressors, they are linearly dependent. That is why that is the multicollinearity exists because of the linear dependence between these two regressors. Now, this additional data should be collected in a manner to break up the multicollinearity in the existing data. Okay, I hope you understood that initially you have n data points, and here x1 and x2 they are linearly dependent. So, you collect another some more additional data, say m data points, in such a way when you combine the complete set of data n plus m data, then x and x1 and x2 are not anymore linearly dependent. You have to collect the data in a manner to break up the multicollinearity in the existing data. Okay. So, this is one way to deal with multicollinearity, or to break the multicollinearity in the existing data. Okay, but in many instances this is not possible in practice. Next we will talk about one more technique to deal with multicollinearity, that is called remove regressors from the model. Okay. Here if two regressors are linearly dependent, it means they contain redundant information. So, what we can do is that if two regressors, for example x1 and x2, they are linearly dependent, maybe for example say x1 is equal to twice of x2, but then I mean basically the information regarding x2 is redundant, right. So, what we can do is that thus we can pick one regressor to keep in the model and discard the other one, right. So, this basically suggests if you have two regressors which are linearly dependent, then you can pick one regressor to keep in the model and you can remove the other one. You can remove say for example x2 from this model, right. If say for example x1, x2 and x3 are linearly dependent, then eliminating one regressor variable may helpful to reduce the effect of multicollinearity, but the problem is that if say for example x1, you have 3 regressors x1, x2 and x3 in the model, and or maybe more regressors, but x1, x2, x3 they are linearly independent, then maybe you can remove one regressor, for example x3 from the model, but to reduce the effect of multicollinearity. But if x3, it might happen that x3 the regressor which you have removed, that x3 might be significant to explain the variability in the response variable. In that case, this removing one regressor may damage the predictive power of the model. Well, so that is why it says that eliminating regressor to reduce multicollinearity may damage the predictive power of the model. So, this is one way to deal with the problem of multicollinearity, and the other technique is collapse variables. So, it says that you combine, if there are linear dependence between 2 or more than 2 regressors, you combine 2 or more variables which are linearly dependent into a single composite variable. So, basically this collapse variables, it says that if you have linear dependence between say 2 or more than 2 regressors, then you can combine those regressors by a composite regressor variable. Okay. So, these are the techniques to deal with multicollinearity. So, one is collecting more data point, and the other one is removing one regressor from the model and combining the regressors which are linearly dependent. Okay. So, that is okay. So, in this module we have learned what is multicollinearity, and this multicollinearity is the name of a problem in multiple regression model. Well, so the problem of multicollinearity arises when 2 or more regressor variables are linearly dependent, right, and and we have learned how to detect multicollinearity if it exists in the data, and also first we learned about how what are the problems due to multicollinearity, and then we have learned how to detect multicollinearity if it exists in the data, and also we learned how to deal with multicollinearity. So, that is all for today. Thank you for your attention.